Welcome to the deep dive. Sometimes the most profound insights come from exploring what seems utterly abstract, maybe even detached from our everyday world. Today, we're plunging into that very space. Pure mathematics. It's often seen as this realm of complex symbols and numbers with, well, no immediate practical use, right? But what if I told you it's the invisible skeleton supporting almost everything we take for granted in modern life?
That's exactly it. That's our mission today. This deep dive will be your shortcut, sort of, to understanding the intellectual adventure of pure mathematics. We'll unpack what it truly is, trace its fascinating origins, explore its core branches, and share the incredible human stories behind its development, because math is very much a human thing, and ultimately reveal its surprising, often foundational relevance to your modern world. We're pulling all this from that comprehensive stack of sources you've provided.
Yeah, and we'll explore how mathematicians tackle problems driven purely by curiosity, sometimes without any practical application in mind at all, only to have their, purest ideas lead to unforeseen breakthroughs that shape our reality. It's quite a remarkable pattern throughout history.
Oh, absolutely. And along the way, we're going to stumble upon some truly human elements. Fierce rivalries, the initial resistance to what were called fictitious numbers,
Yeah.
which turned out to be anything but,
Yeah.
and even a mysterious duel that, well, dramatically impacted the course of mathematical history.
Okay, so let's unpack this. We hear pure math and applied math thrown around.
Oh,
What's the fundamental difference? What exactly is pure mathematics at its core?
right. Pure mathematics, well, at its essence, it's the study of mathematical concepts just for their own sake. It's about exploring abstract ideas,
Yeah.
patterns, structures, really driven by intellectual curiosity and the pursuit of, let's say, universal truths. Think of it as building the most elegant and logically sound theoretical frameworks possible.
Okay.
Applied mathematics, on the other hand, takes those theories, concepts, tools, and uses them to solve concrete, real-world problems. Whether it's designing an airplane or predicting weather or understanding economic trends.
So pure math is like building the engine, maybe, and applied math is driving the car. Is that too simple?
No, that's a good way to think about it. Exactly. But it's crucial to understand that while pure math aims for theoretical rigor, academic advancement, the distinction isn't always a rigid wall. It's not always black and white. It's often more about a mathematician's personal interest or maybe their philosophical approach. Sometimes the purest ideas turn out to be the most practical down the line.
Yeah, that's what G.H. Hardy, the famous British pure mathematician, sort of alluded to. He compared pure mathematics to painting or poetry for its intrinsic aesthetic value, right?
Right.
Suggesting it was about timeless truths, independent of the physical world. But even Hardy, who was a real advocate for useless math, had to admit that his very pure work on number theory ended up being unexpectedly useful. Things like cryptography and computer science. It's a running theme, isn't it?
It absolutely is. The history of pure math is just filled with these serendipitous connections.
Okay, let's journey through that history then. Uncover how this quest for abstract truth began. Where do we first see this distinction, this split between math for its own sake and math for practical ends?
We can trace the earliest signs, really, back to ancient Greece. Think of Plato, the philosopher. He saw arithmetic, and by that he meant what we now call number theory, the study of numbers themselves, their properties. He saw that as suitable for philosophers. It helped them arise out of the sea of change and lay hold of true being, kind of a path to deeper truth. But logistic, which was everyday arithmetic, that was for merchants or soldiers, people who needed to calculate troops or goods, practical stuff.
That sounds pretty snobbish.
It does, doesn't it? And it played out in anecdotes. There's the famous story of Euclid of Alexandria, the father of geometry.
Huh.
A student apparently asked him, rather impatiently, what the use was in studying geometry. And Euclid reportedly told his slave, "Give him 3 pence, since he must make gain of what he learns." Yeah, as if to say, if you only care about practical gain, maybe this isn't for you. And Apollonius of Perga, another great Greek geometer, he asserted that some of his complex theorems were worthy of acceptance for the sake of the demonstrations themselves, basically saying their inherent beauty and logical completeness were their own reward.
So even way back then, there was this push for truth for its own sake. Interesting. But if we fast forward a bit, where did something like algebra, this tool of symbolic manipulation, where did that start to emerge?
Well, the roots of algebraic problem solving are actually surprisingly ancient. The Babylonians, maybe around 1600 BC, were already solving quadratic equations and systems of two linear equations.
Really, 1,600 BC.
Yeah. And the Chinese, much later, around 200 BC, were even solving 3 by 3 systems just by working with numerical coefficients. It was a kind of proto-matrix method, really.
So they were doing what we'd basically call algebra, just without the letters, the x's and y's.
Precisely. Then, around 250 AD, we have Diophantus of Alexandria. His work Arithmetica introduced a partial algebraic notation, moving us closer to symbolic math as we know it. He focused on finding integer or rational solutions to equations, a field that still bears his name, Diophantine equations.
Right. And then, in the 9th century AD, came Al-Khwarizmi. His foundational book, Al-Jabr wal Muqabala, didn't just give us the word algebra, but it clearly showed how to solve quadratic equations using what he called completing the square. He laid out these systematic methods that really transformed problem solving.
And what's fascinating here is how these methods forced mathematicians to confront concepts they initially resisted.
Okay, and here's where it gets really interesting, I think. The reluctant embrace of what they called fictitious numbers.
Absolutely. This problem really kicked off in the 16th century with the quest to solve cubic equations, equations with x cubed. When solutions were finally published by Cardano in 1545, building on earlier work by Del Ferro and Tartaglia, they revealed this, well, unavoidable truth. To get to the real solutions, you had to temporarily use square roots of negative numbers.
Square roots of negative numbers.
Yeah, and Cardano himself deeply mistrusted them. He called them fictitious or sophistic.
So they're essentially saying, okay, we have to use these weird numbers to get the answer, but we don't really believe they exist. That sounds like a bit of a crisis.
It was a huge conceptual leap. And the paradox only got deeper with Bombelli in 1572. He applied Cardano's formula to an equation that had perfectly normal, real number solutions. But the formula still spat out complex numbers, these combinations of real and imaginary parts. This really forced mathematicians to confront these imaginary numbers directly. They were essential tools, even when they seemed to appear out of nowhere just to solve real problems. It showed that mathematics wasn't just about what you could immediately see or measure.
That's a really significant turning point, a departure from the purely tangible, it sounds like. And it paved the way for algebra to become truly symbolic. Right?
It did. The symbolic revolution was really spearheaded by figures like Viet in 1591. With his introduction to the analytic art, he made a crucial move. He started using letters, not just for unknowns like x, but also for known parameters like a, b, c. This transformed algebra from solving specific numerical problems into working with general formulas, made it far more abstract and powerful. Then came Descartes in 1637 with his geometry. He fully standardized our modern symbolic notation x, y, z for variables, a, b, c for parameters. We still use that today. And even more profoundly, he introduced his algebra of segments. Before Descartes, ancient Greek mathematicians insisted on homogeneity in algebraic expressions. What that meant was you couldn't add, say, a length to an area or a volume because they were different geometric dimensions.
Right, apples and oranges.
Exactly. Descartes just broke down this rigid restriction. He allowed mathematicians to combine terms of different geometric dimensions, freeing algebra to become truly symbolic and abstract. You didn't need to visualize everything geometrically anymore.
That's huge. It fundamentally changed what algebra could even represent. And of course, no deep dive into pure math would be complete without talking about the tumultuous birth of calculus.
Indeed. Calculus, the mathematics of change and motion, famously created twice, independently, by Isaac Newton in England and Gottfried Leibniz in Germany during the 17th century.
And there was that famously fierce debate, wasn't there? Almost like an academic war with accusations of plagiarism flying around, national pride at stake in the late 1600s. It's often said that Britain's insistence on Newton's notation, which was apparently more difficult to work with, actually set their mathematical development back for a while.
That's very true. Newton's work, it really stemmed from studies of differentiation thinking about slopes and rates of change, while Leibniz began with integration thinking about areas and sums. Yet, remarkably, they arrived at essentially the same profound conclusions. But what's most significant for us today is that Leibniz's notation, the one we universally use now, proved to be far more flexible and intuitive. That's become his lasting legacy, really.
So his system was just better for exploring new ideas, easier to handle.
Yeah, pretty much. And it's also worth briefly mentioning that the seeds of calculus were sown long before Newton and Leibniz. It didn't just appear out of nowhere. Democritus explored infinitesimals way back in ancient Greece. Ibn al-Haytham calculated volumes in the Middle East. Scholars at the Kerala school in India also made significant contributions. And even in 14th century Europe, the Oxford calculators revived the study of motion and change with surprising sophistication for the time.
Okay, so we've gone from ancient Greek musings to the dawn of calculus and these imaginary numbers. What does this long journey mean for the big picture of pure math today? How did these early ideas evolve into the major branches we see now?
Well, today, mathematics is built upon foundational areas like geometry, calculus, algebra, and real analysis. Those are sort of the pillars, but these have branched out into incredibly specialized fields, often with fascinating overlaps and boundaries that are, frankly, more fluid than rigid. It's a vast, interconnected landscape.
Let's start with the one that literally gives modern algebra its name, abstract algebra. What was the big conceptual shift here? What makes it abstract?
Abstract algebra was a revolutionary step. Instead of just focusing on finding solutions to specific polynomial equations like x squared plus 3x minus 4 equals 0, it started asking, what are the universal rules governing how mathematical operations and structures behave, regardless of what the numbers actually are?
Hmm.
It sought to understand the patterns of patterns. This led to identifying fundamental structures like groups, rings, and fields.
Okay, groups, rings, and fields. For someone who maybe remembers some high school math but isn't an expert, what's the key takeaway? Why are these structures important?
Right. Think of them as blueprints for different kinds of mathematical systems. A group captures the essence of symmetry and transformations. It's basically a set of elements with one operation, like addition or maybe multiplication, that satisfies specific rules, like having an identity element like 0 for addition, and inverses, like negative numbers for addition. It helps us understand everything from the symmetries of a snowflake to the behavior of fundamental particles in physics. A ring adds another operation, usually allowing for both addition and multiplication, similar to how integers behave, whole numbers. And a field is an even more complete system where every non-zero element has a multiplicative inverse you can divide by anything except 0, just like rational numbers, fractions, or real numbers. These abstract structures allow mathematicians to generalize solutions, prove impossibilities sometimes, and unify vast, seemingly disparate areas of math.
And group theory, you mentioned that one first. It has some particularly dramatic origins, right?
It truly does. Évariste Galois, a brilliant but tragically short-lived French mathematician. He played a seminal role. He essentially founded group theory and established the concept of fields in the early 19th century, all before his mysterious death, in a duel at just 20 years old.
20 and a duel.
Yes, one account even suggests only one pistol was actually loaded, as quick as stairs. He apparently spent his final hours frantically writing down his groundbreaking mathematical ideas, convinced he was about to die.
Wow, what a story. And what was his key contribution, technically speaking?
Galois was the first to really use the term group in a technical sense. He identified what he called the group of the equation, which reflected the symmetries and properties of algebraic equations. His most profound invention, though, was the normal subgroup. It's a fundamental concept that helps describe how larger, more complex groups can be broken down into simpler related structures. It's crucial. After him, mathematicians like Cauchy and Jordan systematically developed permutation groups, groups that describe rearrangements of elements. And then Lie introduced continuous transformation groups, or Lie groups, which are absolutely essential for studying differential equations and underpin much of modern physics. Now, if group theory gave us this powerful lens for understanding symmetries, mathematicians soon asked, what happens when we add another operation, like multiplication, to these abstract structures? This led to the fascinating world of ring theory.
And the origin of non-commutative ring theory has its own legendary tale. William Rowan Hamilton's invention of quaternions in 1843. This is the famous story of him suddenly grasping the formula I squared equals J squared equals K squared equals air equals -1 and carving it into Brougham Bridge in Dublin in a flash of insight.
Yes, that eureka moment on the bridge was monumental. Quaternions were the first concrete example of a non-commutative number system. What does that mean? It simply means the order of multiplication matters. A times B is not necessarily the same as B times A.
Like matrix multiplication, maybe?
Exactly like matrix multiplication. That's a great example. This was a radical departure from familiar numbers, like real or complex numbers, where order doesn't matter. And it opened the floodgates for exploring all sorts of diverse number systems that didn't behave like our usual numbers. It laid the groundwork for many other abstract algebraic systems. Now, commutative ring theory, where the order of multiplication doesn't matter, that evolved from different sources, mainly algebraic number theory, algebraic geometry, and something called invariant theory.
Right, and in invariant theory, we have Hilbert's basis theorem from 1890. It showed, with a completely new, very abstract conceptual approach, that any mathematical form has a finite basis. And this famously provoked an older mathematician, Paul Gordon, to exclaim, "This is not mathematics, it is theology."
That quote is legendary. Gordon was a master of the older, more computational methods. He was reacting to Hilbert's highly abstract, existence-based proof. Hilbert's proof showed the basis existed, but didn't give a concrete way to actually construct it.
Yeah.
It was a real clash between two fundamentally different ways of doing mathematics. Direct construction versus abstract proof of existence. It really highlighted the shift towards higher abstraction happening at the time. Then there's field theory, which, as we mentioned, Galois worked on early on. Richard Dedekind later gave an axiomatic definition of a field using infinite sets, which was a truly groundbreaking step in rigor. Dedekind famously believed that the natural numbers are a free creation of the human mind, a very Platonic view. This contrasted sharply with his contemporary, Leopold Kronecker, who held a much more constructivist view. God made the positive integers, all the rest is the work of man. It's a deep philosophical divide about what math is. And Galois also showed that the expressions in his Galois fields, these finite fields, form a field structure, and their multiplicative group is cyclic. These are crucial properties, and these finite fields are now absolutely vital in areas like coding theory and cryptography.
Okay, and let's not forget linear algebra. That probably sounds more familiar to many of our listeners from college, maybe.
Right, linear algebra, the study of vector spaces and linear mappings. It really underpins so much of modern science and engineering, it's hard to overstate. Its roots go way back to ancient Babylonian methods for solving linear equations, sure. But it exploded into its modern form with concepts like matrices, eigenvalues, and eigenvectors, which are fundamental to everything from Google's PageRank algorithm to quantum mechanics.
Eigen what knows?
Eigenvalues and eigenvectors. Essentially, they reveal the fundamental directions or modes of behavior within a linear system described by a matrix. Super important stuff. And a key result here is the Cayley-Hamilton theorem, proved by Arthur Cayley back in 1858. It states that every square matrix satisfies its own characteristic polynomial. Basically, it means that for any square matrix, you can plug the matrix itself into a specific polynomial equation derived from it, and the result will always be the zero matrix. It's a powerful relationship. Hamilton actually proved it independently for quaternions, too.
Okay, moving beyond these algebraic structures and systems, let's talk about number theory, often called the Queen of Mathematics. Why that title?
That title is usually attributed to Carl Friedrich Gauss, arguably one of the greatest mathematicians ever. He systematized the subject with his monumental work, Disquisitiones Arithmeticae, in 1801. He unified earlier discoveries, introduced the incredibly useful concept of congruence, a way to think about remainders and division, which is absolutely crucial for modern cryptography. And he proved the quadratic reciprocity law, which he himself called the Golden Theorem, because of its profound elegance and, well, its deep implications within number theory. But the Queen also had her crises, her tricky moments. The need to solve equations like x squared plus 2 equals y cubed led mathematicians into the realm of complex integers, numbers like, say, a plus b times the square root of minus 2. But in some of these new number systems, the fundamental principle of unique factorization, the idea that every number can be broken down into prime factors in only one way, like 12 is always 2 times 3, that started to break down.
It didn't work anymore.
Not always. Which was a profound conceptual crisis. How could you do number theory without unique primes? To restore this essential uniqueness, Kummer brilliantly introduced ideal numbers. These were abstract entities that behaved like prime factors, even if they weren't numbers in the traditional sense. This concept was later refined by Dedekind through the unique factorization of ideals, putting it on a more rigorous footing.
So it was about finding a way to maintain a core truth, unique factorization, even when the numbers themselves got weird. And that kind of brings us to the very foundations of mathematics itself, set theory.
Right. Set theory is the branch of mathematics that studies sets, just collections of objects. It's a basic notion, grouping things together, that existed implicitly since antiquity. But the real revolution came with Georg Cantor in 1874. His truly revolutionary discovery was proving that the set of all real numbers is uncountable. What this means is, no matter how clever you are, you can never put all real numbers into a list, not even an infinitely long list. They just don't fit. He proved this with his ingenious diagonal argument, which is just a masterpiece of pure mathematical logic.
That's mind-bending. So some infinities are actually bigger than other infinities.
Exactly. That was the shocking conclusion. It blew open the study of infinities. However, this groundbreaking work also triggered what's known as the foundational crisis of mathematics,
Yeah.
because simple, seemingly innocent questions about sets led to inescapable logical contradictions, known as paradoxes, like Russell's paradox.
Okay, what's Russell's paradox? Give us a taste of what created this crisis. It sounds serious.
Okay, imagine defining a set, let's call it R, that contains all sets that do not contain themselves. Seems reasonable enough, right? Now ask yourself this simple question. Does R contain itself? Well, if it does contain itself, then by its own definition, containing only sets that don't contain themselves, it shouldn't contain itself. But if it doesn't contain itself, then it meets the criterion for being an R, so it should contain itself.
Whoa, that's a loop, a contradiction.
Exactly. A genuine logical contradiction derived from seemingly simple set definitions. It shook mathematicians to their core. It made them question the very reliability of their logical foundations. If basic set theory led to paradoxes, what else might be wrong?
That's truly unsettling. So these contradictions forced mathematicians to kind of rebuild from the ground up.
Yes, precisely. These paradoxes prompted the development of axiomatic set theory, building sets on much stricter, carefully defined rules, or axioms. It was like laying down unshakable bedrock to avoid these logical traps. But this shift wasn't universally welcomed. Leopold Kronecker, who we mentioned earlier, famously called Cantor a scientific charlatan, and the philosopher Ludwig Wittgenstein dismissed set theory as utter nonsense. It shows the human, often very emotional reaction to these profound intellectual shifts.
What's fascinating here, though, is how far this field has evolved since then. It even led to something called fuzzy set theory, where an object can have a degree of membership in a set like being zero point 0.7 in the set of tall people instead of just yes or no. Allows for more flexible, real-world classifications where things aren't always simply in or out.
It's a perfect example of how foundational ideas, even controversial ones, can become incredibly adaptable and useful later on. Finally, let's explore the world of shapes and spaces, going beyond simple Euclidean geometry into topology and modern geometry. Fields like algebraic topology, differential topology, and differential geometry. They study properties of geometric structures, often using advanced tools from calculus and linear algebra. They explore concepts like curvature and manifolds.
Okay, what's a manifold in simple terms?
You can think of a manifold as a kind of generalization of a surface, like the surface of a sphere or a donut. But it could be in higher dimensions or have more complex twists and turns, yet locally, near any point, it still looks like flat Euclidean space. These fields look at intrinsic properties of spaces that don't change even if you stretch or bend them continuously without tearing. For instance, topologically speaking, a coffee cup with one handle and a donut are the same shape because you can deform one into the other without breaking or merging anything.
Right, the whole is the key thing.
Exactly. And Felix Klein's Erlangen program in the late 19th century was crucial in bringing some order to this expanding field. He proposed viewing geometry not just as the study of shapes, but as the study of a space, together with a group of transformations that preserve certain properties. This provided a unifying framework that could encompass Euclidean geometry, projective geometry, non-Euclidean geometries, all under one conceptual roof.
This raises a really important question for me. If it's all so abstract and about building these intricate theoretical structures, how do mathematicians actually do pure math on a daily basis? Is it all just sitting down and grinding out logic and proofs from first principles all day?
That's a great question, and it touches on an ongoing philosophical debate about the very nature of mathematics itself. Is it discovered or invented? Some, like the influential Russian mathematician Vladimir Arnold, provocatively suggested that math is just the branch of physics where we don't do experiments. He believed math was deeply connected to physical reality, even if its practitioners didn't always explicitly see it that way.
So maybe more empirical or intuitive than it might seem from the outside.
Not empirical in the sense of lab experiments, but definitely often driven by intuition, analogy, and a deep understanding of patterns. Absolutely. And a crucial concept in how practicing mathematicians actually work, something that's rarely taught formally in schools, is the plateau principle. It's kind of an unspoken credo in mathematical research. You look for and are prepared to use a variety of established results plateaus as starting points for your investigation.
Okay, can you give us an example of how this plateau principle actually plays out?
Sure. Take the Cayley-Hamilton theorem we mentioned earlier, the one saying a matrix satisfies its own characteristic equation. There's a famous one-line proof that looks incredibly elegant and convincing at first glance, but it's actually logically flawed because it involves potentially dividing by a matrix, which isn't always valid.
Hidden trap.
Exactly. Then there's the correct but unconvincing rigorous proof, which is much longer, more technical, involving abstract matrix theory, maybe a joint. It works, but it doesn't always give you intuitive insight. The Plateau principle suggests that practicing mathematicians, once they understand and trust a fundamental result like Cayley Hamilton, don't necessarily rederive the full rigorous proof every single time they use it. They treat that result as a plateau, an established, trusted truth, and then they build on it to explore higher-level consequences and applications. This allows them to make progress faster, to see the bigger picture, and achieve deeper understanding of the consequences, even if at a very strict logical level, it might seem like they're taking a slight conceptual shortcut. It's how they manage the immense complexity.
So it's about trusting the foundations laid by others so you can climb higher rather than, constantly rebuilding the ladder from the ground up every single time. But doesn't that risk building on shaky ground if the plateau wasn't actually as solid as everyone thought? How do they maintain rigor then?
That's a vital tension in mathematics.
Oh.
It's a great point. While they operate from these plateaus for efficiency and insight, the ultimate goal is always rigorous proof. So while a researcher might use a result without rederiving it in their immediate work, somewhere, someone has painstakingly proven it, and that proof has been vetted by the community. The whole system relies on peer review, constant scrutiny, and a culture of seeking out potential flaws. It's this dynamic balance between exploratory intuition using plateaus and the absolute necessity of ultimate logical certainty.
Okay, that makes perfect sense. It also sounds like the boundaries between these different areas of math must be quite fluid then, with all this building on each other across fields.
Oh, they absolutely are. Very messy boundaries, really, with substantial overlap. For instance, there's a famous result called Serres-Gabier theorem. It shows a deep equivalence between certain parts of algebraic geometry, studying shapes defined by polynomial equations, and complex analysis, studying functions of complex numbers. Two fields that seem incredibly different on the surface. Or consider probability theory. Technically, you can define it rigorously under the umbrella of measure theory, which is a branch of real analysis. But their distinct focuses, questions, and goals lead to completely different techniques and, honestly, different cultures among the mathematicians working in them.
So they speak different dialects almost.
Kind of, yeah. It's also why you often see mathematicians organize into informal cliques based on their specific focus, even if their fields are deeply interconnected on paper. An algebraic geometer, for example, might feel they have more in common methodologically with algebra people than with a regular geometer who studies shapes using different tools, even though their overall subject is geometry.
Okay, so for you, our listener, why should you care about all these abstract concepts and the people who ponder them? What's the relevance or the application of this deep knowledge?
Well, the profound impact of pure mathematics on our world is just immense. Even when the initial investigations had absolutely no immediate practical goals in mind. It's like pure math builds this universal language, this incredibly powerful toolkit for understanding complexity in any form. Think about it. In physics, Einstein's general theory of relativity, which describes gravity as the curvature of space-time itself, it relies heavily, fundamentally, on concepts from differential geometry. That's a very pure branch of math that studies curved spaces in the abstract. Without that abstract framework already existing, his theory might never have happened or would look very different.
Right.
In computer science, every time you send a secure message or make an online purchase or log into a secure system, you're relying on cryptography. The security behind almost all modern encryption is built directly on number theory and abstract algebra fields developed over centuries with absolutely no thought of computers or the internet.
So the queen of mathematics is actually securing our online banking. That's pretty cool.
Precisely.
Yeah.
Or take engineering. Topology, that study of shapes that can be stretched or bent without tearing. It's used in designing efficient electrical circuits and communication networks, ensuring optimal flow of information or resources, avoiding bottlenecks. In biology, combinatorics, the math of counting and arrangement, plays a critical role in bioinformatics. It helps us understand genetic coding, analyze DNA sequences, predict protein folding patterns, even the Lotka-Volterra equations, which model predator-prey dynamics in populations. They rely on pure math concepts like differential equations for their very structure and analysis.
Okay.
In economics, mathematical analysis and algebra are used daily in building sophisticated economic models, optimizing resource allocation, understanding market behavior. Everything from supply chains to financial derivatives relies heavily on these mathematical tools.
This is where pure and applied math really join forces then, isn't it? It feels like pure math gives applied math the fundamental grammar to describe the world accurately.
That's a perfect way to put it, exactly. Take epidemiology, which became very visible recently. Applied math models disease spread, right? Mapping outbreaks like COVID-19 to inform public health policy. But it's pure mathematics that develops the fundamental differential equations and the network theories that explain the underlying epidemic dynamics. It provides the deep insights that support those critical decisions. Another fantastic, pervasive example is Fourier analysis. It's rooted deeply in pure mathematics, drawing on real analysis, functional analysis, abstract algebra. But it's this incredible technique that allows mathematicians and scientists to break down any complex pattern or signal into simpler underlying waves or frequencies. Today, it's absolutely essential and feels like signal processing, allowing your phone to understand your voice commands amidst background noise. It's used in image compression, that JPEG photo on your screen uses Fourier-related ideas. In audio engineering, allowing for noise cancellation and sound manipulation. And even in quantum mechanics, describing the wave-like behavior of particles, all from these abstract mathematical ideas about waves and functions.
Wow. And beyond these specific applications, just studying pure mathematics equips you with these highly adaptable and valuable skills, right? We're talking analytical thinking, rigorous logical reasoning, sophisticated quantitative analysis, powerful problem-solving abilities. These are crucial skills that are highly valued in all sorts of diverse industries, from finance to technology, healthcare, even law or consulting. It's truly a foundational intellectual training, it seems. So we've journeyed from ancient paradoxes in Greece to modern abstractions like manifolds, from the grudging acceptance of fictitious numbers to the elegance of group theory. This deep dive has explored the intricate beauty and, maybe surprisingly, the profound utility of pure mathematics. It's clearly a field that's constantly evolving, driven by this deep curiosity and a desire to understand the fundamental structures that govern not just numbers and spaces, but perhaps, in some sense, reality itself.
Yeah, our deep dive into pure mathematics really reveals that its abstract nature isn't a limitation at all. It's actually its greatest strength. By pursuing truth just for its own sake, it provides the language and the tools to solve problems we haven't even conceived of yet. It truly shows that there's often nothing so practical as a good theory.
And perhaps, as that story of Bombelli and the cubic equation suggests, sometimes the most fictitious or abstract ideas can lead us to the most profound and useful realities.
Absolutely. So here's a final thought for you, our listener, to ponder.
Hmm.
If, as some mathematicians like Arnold hinted, maybe all branches of math are just different ways to approach ultimately geometric problems, what fundamental geometric problem, maybe metaphorically, are you working on in your own life or work? And with seemingly abstract tools or ways of thinking might actually help you solve it.